Hey guys, welcome back to my YouTube channel. So today we are going to discuss what is mean by canonical form and how we can derive and how we can get that for each function. So last class we see about min term max term. So which is nothing but a representation for a function. So if you see an XOR function, XOR logic gate function can be represented in two ways. That is one with min term and another one is max term. One is SOP and another one is POS. Okay. So this is with respect to min term and max term. So how we can with this can be even written SOP. So that is what this is a bar b plus a b bar. So this is how we can. So we know this is the actual logical function for this one. So if we return this is in a POS, then it is a plus b product a bar plus b bar. So this is how we can represent the same function in this one. Here it is nothing but they are taken a whole bar. So that is what this one. So both are even duality to each other. So both is like a complement to each other. So let's see what is my canonical term. So canonical form. Each term must contain all the variable in either normal or complementary form. So that is what the canonical form. So canonical SOP or POS, which is nothing but it's need to contain all the variable which are present in that system. So for an example, if f is a function of a comma b comma c, okay, and we are having this function ab plus a bar c plus abc. So here you can clearly see this is a function of abc three variable, but here we are seeing only two variables. So this is what the term that the canonical term is implying that here this is not a canonical form. This is not a canonical form, non-canonical form. Okay. So if a function a comma b comma c, which is equal to a bar b bar c plus abc plus a b bar c. So this is canonical form. So that is what it implying that it need to contain all the variable in it. So how we can convert a non-canonical form into canonical form? The thing is that, so let us take an example that f is a function of a comma b. So let's take a simple case. So which is a plus b, a plus ab, like that I'll have. So here the thing is not b is not present at here. So what we can do is that we have to multiply with b plus b bar plus ab. We know that b plus b bar is equal to 1. So 1 into a is nothing but a. So that won't affect the function of the system. So if we multiply this inside, then we get ab plus ab bar plus ab. So as ab is mentioned twice them, if we add them, that will be equal to ab only. So ab plus ab bar. So here what the thing is that this is canonical form. So we have added a one small note, instead of 1 we have added this to b plus b bar, and we are converting this from non-canonical form to canonical form. So this is how we can convert from non-canonical form to canonical form. So now even we can derive this to be if we need to write in a min term, this is equal to the a which will be termed as a which is termed as m3, and another one which is a bar b, sorry a b bar. So a b bar is m2. So if we need to write this one, then we can write this as a 2 comma 3. Okay, so these are some kind of representation that we can follow. Even this complex logic function can can be write like this one. So that is what we are trying to state here. So I hope you guys have understood some idea over here. So in the sequence of lecture we will be understanding more things like that. So let us take another one example to how we can convert from the non-canonical form to canonical form. So it is a function of a comma b comma c. Okay, so let's take up POS. So a plus b bar plus c, that is product of sum, so it will be like this. So a plus b, so let's take a plus b. Here c is missing, right? So let's take the case a plus b bar plus c dot a plus b plus c bar, because c bar is 0, so 0 plus anything that will return this value. So we are writing this like this. So now let's split. So what we have to do is that we can split this among this one. So as we can see another one product here, so we can split this among. So we can like write that. So if we done like that, then that will be equal to a plus b bar plus c dot a plus b plus c a plus b plus c bar. Okay. So we clearly can state that which is equal to 0, 1, 0, 1, 1, 1. I'm just naming that bar is there. I'm mentioning it as 1 and normal it is mentioning as 0. Sorry, here it is 0 because we are mentioning this in max term. Alright. So in max term, no, without complement is 0 and with complement is 1. So if we write the thing that is equal to mm, then this is 0, this is 1, this is 2. So 1 comma 2. Similarly, for previous case also we can write. So this is equal to here we will represent same as it is. So which is 1 0. So this is 3 and this is 2. So that's why we have represented here. The same thing we have mentioned here. But you have to be very careful to name this one. So when in POS we will be stating if it is a normal thing we mention at 0 and the complement things we will mention at 1. So you have to be very careful on those representation. So I hope you guys able to identify know how to convert from one form to another form like non-canonical to canonical form. So here I am giving you one hint. So if there are n Boolean variable means the a comma b comma c I am saying that. So that is what. If there are n Boolean variable in a function, n Boolean variable in a function, then 2 power n. So this much Boolean functions we can get it. Of Boolean functions we can get it. So this is one of the very important thing you have to remember. So please make a note of it. It's not 2 power n, it's 2 power n. Okay. So we have to come from the top. For an example, if you have n is equal to 2, then 2 power 2, then 2 power 4. So 16 types of things we can make it. So 16 different types of function we can write. For an example, if n is equal to 2 means we can make a different functions like a, b, 0, 1, ab, a bar. So like this way. So this much the different combinations of different types of function is what they are suggesting. So that will be 2 power 2 power 2 which will be equal to 2 power 4 which will be equal to 16. So 16 types of things we can write it. So this is a very important one mark that already they asked in IES as well as in GATE examinations. So please make a note of it. So now we have seen the SOS, POS, everything. So what are the help of this one? So why we need to study and with this what we can do? So that is what K-map is the thing. So K-map is the concept where we can use this min term, max term to represent our function. So where instead of finding this with our here if you see we have used a trick to convert this from one form to one form, and in other cases we need to use our skill to find out the or minimize the variables like minimize the Boolean function. Like that way this kind of questions will come. For an example, if a b plus a bar c plus bc, if they ask to simplify this Boolean algebra, simplify this Boolean function, simplify the Boolean function, then what we can do, we need to use our tricks to solve. So an example how we can solve is that, so ab plus a bar c plus bc, that I'm adding a plus a bar. Okay, because the a is missing here, I'm just taking one term, so a plus a bar is missing. So if we add this one ab plus a bar c plus bca, I'm rewriting down abc, so abc plus a bar bc. Okay, so let's take this term. So here we can take a bar c as a constant and here we can take ab as a constant outside. So ab, then 1 plus c will be the term, so this 2 1 plus here a bar c, we are taking this 2 1. So if we take it outside, then 1 plus a bar. Okay, so sorry, 1 plus b, 1 plus b, right? So if we take the thing 1 plus anything is 1, so we can ignore the thing. So this will be simplified to a b bar c. Here you see the 3 term Boolean function now can be represented even in 2 function, 2 variable. So because this is a simplification of Boolean thing. So here we need to use our skill and analytical things to find out this thing. So everybody cannot do this like easily. If we done many mistake, anything mistake, or even if we put here b plus b bar c, even it will give some 5 or 6 more steps to get into answer. Anyway, we will get into answer, but that will may result in different types of Boolean things also. So that is not needed. So if in case of K-map, we can minimize it very perfectly. So for that only, we are discussing about min term, max term, and now we are going to implement the same in the K-map. So let's see how we can use in the K-map. So let me start with the what is mean by K-map and what are the functional purpose that we have getting from K-map. K-map is Karnaugh Maps. Karnaugh Map. Okay, they will always also call us which diagram. So which diagram is the another name that you can use. So K-map used for minimization of logic. So now the many very important thing is that minimization of logic without any difficulties or any analytical skill needed. Minimization of logic function. So minimization of logic functions. Okay, so this is the one condition. For an example, if we are having a binary number which is converting into a gray number or any kind of things, we need to be we will be having some kind of logic there. So from that logic, we can able to get the functionality output. So with that function, we can draw one kind of box, that is what the K maps. This is a diagrammatic representation box. So let me start with the two variable K map. So let's take two variable K map. Okay. So let me draw it. So this is how this is standard procedure that they gave. So this is like with this only we have to draw the K maps. So I'm separating this to 2 and then 2 to 4. Okay. This is as it is two variable A and B. So the thing we have to represent is 0, 1, 0, 1. Okay. So let me copy this to two more sections. Okay. So let's go each by. So here, this is how we will be having, this is with the SOP, the sum of product if we take. So 0, 0 which will be represented as M0, 0, 1 which will be represented as M1, 1, 0 will be represented as M2, 1, 1 will be represented as M3. Okay. So if we get the function output, for an example, if A comma B as it is two variable, and we get summation of M which is equal to 0 comma 1 comma 2. So here if you see, at these all are the values, the function which is equal to 1 from the K map, like how from the logical gate we know, right? So this is some kind of this is actually some kind of logic or logical gate output that they have given us. So the at 0 the output the function this function the boolean function variable may be anything, but that is represented in a SOP format. So that function, when we apply 0, 0 as input, the output will be 1. So that is what 1. 1. So when give 0, 1 as input, the output will be 1. 2. When 1, 0 which is given as output, then output will be 1. Okay. So this is the thing. So how we can get a Boolean function from this one? Actually, this is standard. This is only one. So this will be unique. For a function, this will be unique. So only one which will be unique. Okay. So how to get the Boolean function from this SOP or the POS things? So here there is some rules to be followed. The rules of grouping. So take a grouping of maximum possible adjacent cell. The priority is that if we find 8 cell as the grouping, we have to map it. If we find 4 cell as a grouping, we have to map it. Then 2 pair and then single term. Each min term must be covered at least once. Each min term like this, each thing need to be covered in a grouping. We can remove the redundancy. So these are the three things we need to remember. So now let's see how this can be grouped. So here the only 2 is the maximum that we can group. So here this one can be this one can form adjacency with this one. This one will also form adjacency with this one. Okay. So if we consider this one, all the min terms are at least covered in one of the grouping. So the rules is now done. So the thing we followed the priority. So the first rule is that priority. So we have followed from 8, 4, 2. So 2 is the maximum that is we can do here. We done it. Then each each min term need to be covered at least once. So that also we have done. Then we can remove redundant. So I think here there is no redundancy. So here now see how we can write the functional mapping. So first let's consider this one. So here if you see the B is varying 0, 1 both thing is there, but A is constant. So A is only 1. So we can directly write which is A bar. So next implement, the first implement which is we covered. So here there is only two circles are there. So the first circle we have covered it. So which will result in A bar. as it is covering only one constant variable, so that only we have to take it into account. So if the second grouping is this one. So if we take this one, A is varying but B is constant. So we are taking, as this is an SOP, so plus B bar. Okay. So I hope this is understood for you guys. So this is how we need to group it. For your understanding, let me take another one example. So here it's another one function of A comma B. So which is equal to summation of M 1 comma 2. Okay. So 1 means 0 1, 0 1 is 1, and 2 means 1 0, there it is 1. So here let's see how we can group it. Here if you see, the diagonal crossing is not allowed, only the adjacency group. So here if we find a 2, 8 is not fair, 4 is not there, 2 grouping is also not possible, so only one grouping is possible. So it will individually forms a group. So there is a 2 grouping that we have to do. So thing is that F is equal to, here I say only one. So this is also fixed, this is also fixed. So we have to write that one. So which is A bar B plus, for this grouping, this is also fixed, this is also fixed. So which will be A B bar. Okay. So this is how we have to write the function. So if we can check this one also. So here we know the functional output will be 1 when we apply 0, 1 and 2. This is two variables, so 0, 0, 0, 1, 1, 0. If we apply this input, if we apply 0 here, 0, 0, both will be turned to 1. So output will be 1. So if you know here, here also output will be turning to 1 because as it is A complement is 1. Here B complement will also turn to 1. So this is what they mentioned there as 0, 1, 2, 3. So here also, if you apply 1 and 2, which is nothing but 0, 1, 1, 0. So this is an XOR gate function only. So it will be 1 at these functions only. So this is an XOR gate. So this is an XOR. So this is some different. So we can even name it as A, B, the whole bar. Like that way also we can. So this is NAND gate logic. So NAND gate logic. Here if you see, we have get these min terms, the presence of 1 at the output from the truth table, and we are finding the exact Boolean function from using K-map. So we haven't done it manually. With the K-map we are doing. For the simple two variable, we can even manually do this one. So we can even directly do, we can manually do this. But with 5 variables, 6 variables, 4 variables, even 3 variables, it will be very difficult. So we have detailedly discussed about two variable K-map in this one. So in this next video, we will be discussing detailedly on the 3 variable K-maps. So I hope this is very informative for you guys. So feel free to add your comments over there if you guys have any disturbance or any kind of understanding disturbance. So please let me know. I will clear it. Thank you. Stay tuned, guys.